Okay, hello everybody. So this is going to be the last lecture that we're going to be going over for chapter 7. And so in this lecture, we're going to be talking about comparison between the four reaction mechanisms. So this is going to be a little bit different lecture. And what I'm going to do is I'm going to try to do this in a flowchart format. And I know the book has kind of a grid, and that works too, but I kind of like the flowchart format as well. So we're going to kind of go through this because the number one question I get about all of these reactions when you're trying to make this determination about, well, is it SN2, is it SN1, is it E2, or is it E1? The question I always get is, well, where should I start? What should be the very first thing that I should look at in a reaction when I'm starting to make this determination? And there are several approaches to this, but in my mind, your very first thing that you should be looking at, okay, and asking yourself is, do you have a good leaving group? Okay, because this is really required for all four of these reactions. Okay, now if you don't have a good leaving group, well, that doesn't mean you're dead in the water, because the next question I'm going to ask is well, all right, if you don't have a good leaving group to start with, is can you make a good leaving group? In other words, is this something that you could maybe protonate an acid like an alcohol? So can you make it a good leaving group? And we're going to see this also in the future as well, because sometimes there are things that you can put onto things that are bad leaving groups and turn them into good leaving groups. Well, if you come away from that and go, well, no, there really isn't anything that I can do to make it a good leaving group, well, then more than likely, you're looking at something that's a no reaction situation, at least as far as those four are concerned. And that is a possibility in here, is that you may sometimes get no reaction. Now, if you come away from this and you're like, well, yes, I do have a good leaving group. Well, then what should be the next question that I ask? Because that's more than likely given in most systems. Is, well, do you have a good nucleophile / base in the system? Do you have a good nucleophile or base? Well, if the answer to that question is no, then the very next thing you should be asking is well, is a carbocation formation possible? Can you make a carbocation? Okay, and again, remember, rearrangements can occur here if it is. And so you may not be able to make a good carbocation to start with, but it could rearrange into one. And so you have to kind of think about that as a possibility. And this also kind of ties in above too, is that if you can make it into a good leaving group, well, then you should be asking yourself this question as well, can you form a carbocation? If carbocation formation is not possible, well, then this is again not a dead end, kind of a no reaction situation. But if carbocation formation is possible, okay, yes, well, then we're looking at SN1 and E1 as a possibility, okay? And again, remember that heating will help you promote elimination in that instance, okay? Now, if we back up to this point and say, okay, I had a good leaving group, yes, but I also have a good nucleophile and a good strong base. Well, then the next question I'm going to ask about that system is, are there sterics in the nucleophile / base? Are there sterics in the nucleophile / base? Well, if the answer to that is yes, there are sterics in the system, well, then if you have beta hydrogens, that are present, then this is going to promote an E2 elimination, okay? If you do not have any beta hydrogens present at all, well, then you're looking at, again, a no reaction. Now, I'm going to carry this thought here, process. So you do have beta hydrogens, yes. Then the very next thing that you're asking is that, well, are there sterics in the system with the leaving group, in the substrate, okay, as well? Well, if there's sterics in the substrate, thing attached to the leaving group, yes. Then you're looking at the Hoffman product here. Less substituted as the major, okay? No, it's not very sterically crowded. Well, then you're looking at the Zaitsev, okay? Less the most substituted alkene as the major. But you probably will see both of them, okay, in a given system. It's not exclusive. All right, now, so having gone through all of this so far, you know, that you may be thinking, well, okay, well, where is SN2 fit into this? Well, SN2 is actually a very specific set of conditions. You have to have a good leaving group, you have to have a good strong base, and there cannot be sterics in the nucleophile, or it won't work. And even after that, then you're asking yourself, well, what kind of solvent? Do you have a polar solvent present? Okay, now it prefers to be aprotic. Yes, in fact, it does need to be a polar solvent. Then you will expect to get SN2 to occur. But if the polar solvent is not present, well, then we're back to a no reaction situation. Okay, so it's going to be difficult for that to occur without having that polar solvent. So SN2 really does require a lot of specialization. Okay, so exceptions are possible. Exceptions are possible, so be careful. Look at each system carefully, make sure that you're not missing something that stands out. This is just kind of a guide, a roadmap to help us as we're starting to look at, you know, having to consider, you know, every type of reaction that we've discussed so far. So I want to predict the products of the following reactions and indicate the mechanism that produced that product. In other words, was it E2, was it E1, was it SN1, or was it SN2 for each product produced? Okay. So first question we'll look at Come into focus. Sorry about that, guys. There we go. And overload. All right, so let's say we have this alkyl halide, and we are going to treat that with a bulky base, terbutoxide, terbutanol, heat the system up. Okay, so we're going through our mental checklist. Do we have a good leaving group? Yes. Okay, we do. Do we have a good, strong base nucleophile? Yes, yes, we do. Are there sterics in that? Yeah, there's definitely sterics in here. Do we have beta hydrogens present in the system? Okay, so we have, this is the alpha, so there's beta, so there's a hydrogen there, and there's a hydrogen here. Okay, yes, there are beta hydrogens present. Well, then you're predicting this is going to be it's going to be an E2 elimination. But considering this, are there sterics associated with the system? And I would say, yes, there is sterics in the system because you have a lot of groups surrounding that iodide. So this is a sterically hindered compound. So you would expect to see some elimination of that red hydrogen to give you this product, so the terbutoxide eliminating here, versus, say, this hydrogen over here, that you would expect this one to be the major product, the Hoffman product, because of the sterics in the system, and that this is going via an E2 mechanism for both products. Okay. All right, let's try another one. So this one will make something look a little bit weird here, but just bear with me. So we got this crazy looking thing here. Okay. And I'm going to treat that with sodium iodide and acetone. Now, starting at the very first question here, do I have a good leaving group? You may look at this and go, well, that's not a halogen. How do I know if this is a good leaving group or not? Well, the answer to that question is well, if the electrons go oxygen, can this thing stabilize it? And the answer is yeah. You've got lots of resonance stabilization, and you've got those electronegative fluorines on the carbon as well. So this is actually a very good leaving group. This whole thing is. So this is what's referred to as a triflate. Okay, and so those are good leaving groups. And that's one of the things you can turn an alcohol into to turn it into a good leaving group. And we'll see that in chapter 11. Now, do I have a good nucleophile? Yeah, iodide is a fantastic nucleophile. Are there sterics in this associated with this system? Okay, well, not really. Not a whole lot of sterics here. This is secondary. And iodide is one of these systems that's a good nucleophile, but a poor base. Again, remember that HI is a weak acid, or excuse me, is a very strong acid, so iodide is one of the weakest bases out there. But iodide is a great nucleophile because it's large. So it's able to get in and kick out that leaving group. And you can see how it kind of cascaded the electrons to show that that can happen. So if it's going to do that, then this is predicting an SN2. But how should I draw the iodide in the product? Well, it should be drawn with inversion of configuration because that was a stereosphere. So this should now be coming towards us, okay? And then your triflate ion, which I showed a resonance structure of, can go off on its merry way. Now, let's say I took this compound and I now decided to treat that with cyanide. Well, again, you know, cyanide is a good nucleophile, iodide is a good leaving group, so you would predict this is going to do another SN2 reaction. Well, what would that product look like? Well, now the cyanide would be in the opposite direction of that. You get inversion of configuration a second time. And so you're seeing SN2 reactions occur here twice. And this is a good way to control configuration by doing sequential SN2 reactions. Okay, let's look at one more example. Okay, so I'm going to take this alkyl halide, I'm going to treat it with methanol. So we've got a good nucleophile there, yes. Excuse me, we have a good leaving group there, yes. But we don't have a good nucleophile or base. This is actually a poor base slash nucleophile. So if you remember where we were in our chart, good leaving group, yes, but not a good nucleophile base. Well, then the next question is carbocation formation possible? And the answer is, well, yeah, it is possible. You can have that leave. Now, when that happens, what happens to your stereochemistry? Well, your stereochemistry is gone. So now methanol can do one of two things. If I didn't indicate heat, you've got to assume that we're not heating it up. And so potentially what could happen here is that you could get the methanol deprotonating this hydrogen here. So we're starting to see some of this product. Or this hydrogen here in blue. So we're starting to see this product, both of which are E1 eliminations, albeit this one is the major of those two. But there's going to be another set of products that's going to come from the methanol coming in and actually just adding directly into that system. And when it does so, you're going to get two possible products, okay? So let me just go ahead and draw it out so that I'm not indicating this initially, so we can get rid of this acidic hydrogen. This is definitely a stereo center right there. So we got that hydrogen right there. Go ahead and get rid of that. And so now the products that we're going to be drawing out here, I'm going to show each stereoisomer, is we're going to be getting one where the O-methyl is coming towards us, and one where the O-methyl is moving away from us. And which one of those do you think would be the major product of those two? And if you said, well, there won't be, you are correct, because this is a racemic mixture. And that's going to be difficult to resolve that, okay, that racemic mixture. So that pretty much leaves us with this big mess. And now I want you to see that this is not practical reaction. This is not something you would want to do. First, you've taken a pure compound that has a pure stereocenter in it that is of one particular configuration and turned it into all of this stuff. So this is more of a cautionary tale, and something to consider is that SN1 and E1 reactions are really not all that great because of carbocation formation and because of multiple products being able to be formed. Okay? All right, so that pretty much gets me through all of the material that I wanted to say about Chapter 7. So if you have any questions or concerns about this material, again, please feel free to comment in the comment section or send me an email. I will say that this is the most common question I get asked about in Organic 2 is how to do this type of chemistry, to do this comparison between SN1, SN2, E1, and E2. And I don't want you to think that this is easy or a trivial afterthought. This is requiring you to know quite a bit of information in order to come to these conclusions. So this is where you've got to make for sure that you're doing your homework and that you understand really what is being said, because where it starts to get hard is where they're no longer just isolating reactions and you know it's doing a substitution. Now you don't know what it's doing. It's completely open-ended. So it gets to be a little bit more of a challenging problem. Okay, but I'm sure you guys are already aware of that. So with that being said, that concludes Chapter 7. We will begin talking about addition reactions in Chapter 8, and we will be seeing more of alkene and alkyne chemistry in those chapters and chapters to come. Okay, everybody take care, and I will see you in the next video. Bye-bye.